So I think that it's time to start. Thank you and welcome to this workshop. The title of this workshop is Data-Driven Smart Buildings. And my name is Diego Arnone, and I'm a senior researcher and technical manager for Ingegneria Informatica, an IT company in Italy and all over the world. And here I will be the moderator of this workshop. And I'm also the coordinator of one of the two projects that promoted this workshop, in particular DigiBUILD and DEDALUS, together with Sofia Mulero, that is from Cardiff, coordinator of the BuildON project, and Christian Pozza from Iraq, that is coordinating the Moderate project. So the four projects that have promoted this initiative because we think that talking all together about relevant topics related to the data-driven smart buildings could be interesting for all of us. So basically the workshop is split into sessions. The first one will last 1 hour and we will start soon with the presentation. Then the second topics will be split in two subsections because of logistic and organizational needs. So we will start during this first part of the workshop with the first part of the second session. So we'll have there's a first part before the coffee break and the second part after the coffee break. And at the end of the workshop, we will have a panel discussion. If strictly necessary, you can ask questions at the end of the presentation, but I would suggest to keep your questions for the panel discussion, so you can take notes, and then at the end of the sessions, you can talk to the experts and ask what you need to ask. So I think that I've taken enough time, so I leave the floor to UCL. And in particular, I will leave the floor to colleagues that are working both in DigiBUILD and in BuildON project. So we will see a presentation that is a short introduction about the main topics that you are addressing in both the project, but then we will go in details separately in BuildON and DigiBUILD. So I give the floor to Flavia De Andrade from UCL and Dimitrios Rovas from UCL too. And so the floor is yours. Please, you can take also this.
Perfect. Thank you, Diego. So very happy to be here and open up our session on interoperability. Dimitrios and I here are going to be talking about two of the projects that UCL has been involved with, BuildON and DigiBUILD, and basically focus on how we are approaching scalability and portability of smart building applications using semantic models and ontologies. We start the presentation with an overview of what we mean by portability from a computer science point of view, and then semantic models, and then Dimitrios will present DigiBUILD and the tools that we have been used and proposed for extend existing ontologies and created semantic models based on them. And I will present BuildON architecture on how we are leveraging those semantic models to actually deploy analytic and control applications. At the end, we are going to have a demo. So portability, if we look at the mobile industry, can be seen more clearly in this plug-and-play behavior. Let's say that we want to develop an application. It may take X months. If we want to deploy it in different cell phones, it may take like 30 seconds. We just need to download them. These cell phones can be from different operational systems. They can have different features. And let's say that we need to do that for 35 million phones. It might take 30 years. It may sound a lot, but if we look at the mobile industry, what typically happens is that we develop an application, X months, and then we deploy that in a building. When we need to move on to another building, we might have to start all over again and take those X months again. So if we need to do 35 million buildings, which is actually the number that is needed to renovate a number of buildings that need to be renovated by 2030 in EU, it may take like million years. So current practice is actually not scalable. And why is that? And this is what we are looking at in this presentation and in the different projects. For one, mobiles are not the same as buildings. So if we go to the buildings, we ended up having a lot of heterogeneity. Every building is a prototype. No two are going to be alike. The first part is that apart from having different data source, different formats, different protocols, different vendors, we also have building-specific and very customized design systems. Those lead to two main problems: the lack of interoperability on the technical level. We have lots of data silos, and to communicate the different data source, we ended up with this spaghetti arrangement, where we have ad hoc and this point-to-point connection. We may say that standard communication protocols can partially help and address this, normalizing the data at once, but we also have the other problem, that is the lack of semantic interoperability. And by this, we mean having the meaning of the data. We are able sometimes to integrate it with the communication protocols, with the data, but we don't know what the data actually means. The metadata, those labels that are used in different buildings, they can be very informal, very customized, and we need the help from the building experts to interpret them. And here is an example. If we just look at this point name, we might not know what it is if we don't actually dig it and understand what is the convention behind it. So that is where semantics comes in, semantic models, to try to help this problem with the semantic interoperability. And we can see semantic models as data models that can be built on top of ontologies, formally describing different classes, different relationships, different points. Here's an example. So we can have one building, and that building can be represented in a standard way by a specific ontology, instantiating a specific ontology. In this example, we have a brick as the ontology, and we can see our handler unit being connected, feeding a VAV box that has a couple of device sensors, set points, and that has a relationship with a zone. So using those standard conventions and those standard relationships, we can facilitate the way that application developers can interact with the building and discover the data points in the building. And we do that using a method called ontology-based data access, that it basically has add a conceptual layer on top of the different data source to allow the different applications to communicate it with the buildings. It allows this unified data access, which can help the applications to be self-configured. So we can basically use similar queries to be generated automatically based on the requirements of each application and interact with, by the same time, with different buildings, which could ultimately create what there is this saying, or this process, this approach of developing once and deploy anywhere, and where we look at reducing costs and relying less on this human assistance for interpreting the data points. That is the context, and now Dimitrios will present a little bit how we are actually using in the tools that we are developing to support this application.
So hello from myself as well. So I'm a colleague of Flavia, and we are both working on those two projects that we'll be talking about. So DigiBUILD is a project that started before BuildON, and engineering, and Diego is the coordinator, but there's 17 organizations, 11 countries, and 10 pilots. And I think that kind of sets the context of the challenge, that we have a very diverse set of buildings that we need to work with, and we need to be able to develop and deliver services that support data-driven monitoring of building stock performance. So we're not going to be talking in this session so much about the services themselves, but what we can do as a way of processing and extracting information about the buildings, how we can normalize that information so that it can become accessible by the applications and usable by the applications. So if I might start by setting the problem, I mean, the main problem is that if we look at each building that we work on or live in, each one of them tends to be different. And it is different in many substantial ways. The geometric aspect can be different, configuration aspects can be different. When we go into MEP, it can be different. And then we have, at least for commercial and larger buildings, some sort of infrastructure related to monitoring, which is required for the building operation, but also to understand how the building is actually performing. Now, the problem is that we have all this potential information, and the ambitious idea is that we might have some sort of structured data model, some sort of Revit data model, or IFC model, especially when it refers to the geometric context. But in many other contexts and many other domains, it might be that that information is not there or it is missing. So we have all these data sources or potential data sources. Some of them can be structured in multiple different ways, and some of them can have information which is inconsistent or sometimes even imperfect. So the main challenge that we're trying to understand is how can we take all this information and kind of mass them up together and generate some sort of normalized representation that doesn't need to be as rich as a BIM model could be in terms of information content, and make that information to a good level of detail so that it can be not the perfect information or the perfect amount of information or the full detail of the model, but rather information which can be useful into supporting application development and deployment. So the main idea is an idea of sufficiency. We don't need to do something, we don't need to extract everything, but we just need to do the best that we can with the available data that we have. So the main idea, and since we're a session about data models and ontologies, is that we can use reference models and reference ontologies. And in this particular domain that we're working into building operation, there's already quite a lot of them that can be used and reused. So we've put a few of them there, like the work of the League Building Data Group, BRIC, Web of Things, Real Estate Core, and there's many, many others, and we have a report from an IEA project that kind of summarizes the state of the art on that. The main idea then is that we can maybe take that information, assuming that it is imperfect, try to do our best to generate and instantiate that graph. Depending on the level and quality of information, the graph might be looking very different. But then once we have done our best, we can have a normalized structure that can be the same as a structure. Obviously, the specifics are going to be different across buildings. And therefore, the first part of the interoperability and the separation is that we have this ability or the capability to have graphs that follow the same structure and therefore write queries based on that structure, and then apply those queries into different graphs that follow the same structure for different buildings. And that is something which is quite standard and is quite common in this domain. The part is how do we work with all the data. And then once we're able to do that, then that aspect of portability comes in, that we can have applications that relate to monitoring and benchmarking, to assessment and fault detection, forecasting and prediction, optimization and control. And these services can say or manifest that to be able to forecast, for example, energy consumption on the following day, for example, for purpose of control, I need energy data at the building level over a period of that amount and with that frequency. And if that data is available, then potentially one of these services can be applicable and can be deployed. But the main point is that once we write that service once for one building, then we can take that same service and install it in the way that Flavia was talking about before in another building, and assuming that our data is there and the information structures are there, we should be able to do that. So this is what we're exploring in DigiBUILD. And as I mentioned, that idea or that concept of sufficiency is paramount. So we started by looking at the domains and questions that we would like to ask our models. And we have pilots that are very diverse. So we have pilots that focus on classical O&M, a building with heating and cooling systems, quite large and quite complex, and we're going to talk about this. But then we might have district heating networks, PV systems, battery charging, and so on. So the first part, and one that I'm not going to go so much into it, is understanding those information requirements and capturing those information requirements and developing that ontology. Now, I don't want to say that this has been the main focus, or this has been the bigger focus, because we try to do what is common practice and use or reuse existing ontologies, because that facilitates interoperability and that facilitates reuse. So we looked into aspects like BRIC, which is used quite a lot, ASRE 223P, which is a standard which is emerging from ASRE, and then other related ontologies that are relevant to this domain and are used quite widely. Now, the next step is where it starts becoming more interesting. And in many approaches, people are saying, give me the perfect data, or give me as much data as you have, or give me all the data that you have, and then we can start working on it and making them better. We're going to find issues. We're going to try to match them and make them consistent. And this usually is a good process because that improves the data quality, but it is also a tedious process and one that takes quite a lot of effort and quite a lot of time. So the idea is maybe if we can flip that question and kind of say, give us the data that you have available and we'll try to do our best to get as much information out of them as we can. And if we can't find some information, we should notify you so that you can go back and either look at your data or provide more information or both. And so the main idea of the process is the following that we're implementing is that we have different data sources, and these data sources can be structured data, as could be exported from a PLC or from some other standard like COBE. We can have more structured models like BIM models, and these don't exist very often, and when they do exist, they're not of very good quality. This is our experience. And then we can have other information that might coming from secondary systems or secondary domains like heating and cooling design systems. And so each one of them represent one representation of a specific facet of the building, and it is quite often focused on a specific domain. So the main part here is the following, is how can we take some of that information, ingest that using ETL tools, extract, transform, and load, and populate parts of our ontology, and then combine them together to create that knowledge graph. So what we have been focusing on such workflows. And this is one example. For example, this is looking at the UCL building. This is the MEP side of the IFC, and these are maybe the more complex ones. And by taking that and looking at the MEP side of that model, we can infer connectivity and then populate a knowledge graph to have supply and other aspects, and that populates that one part of the graph. Or we can be taking information from similar models and looking at the spaces. We can use that to generate the geometric part of energy models. This is called second-level space boundary topology, and we have been doing that in the context of running Energy Plus and Modelica simulations. Or we can generate the topology, which is very important into understanding that information. And that happens algorithmically on the back end. And then what we have been developing within the project is this data integration middleware that allows us to plug all these components. And therefore, whenever we want to add a new functionality or we have a new data source that has a specific structure, we can develop another component and then use this in a flexible way to take and ingest the data and then populate those knowledge graphs. So we have been developing this over a sequence of projects, and this kind of takes and helps ingest all the data and bring them and populate parts of that knowledge graph. These are examples from some of the pilots that we're working with. Some are using BIM models, some are using automation data, and other information that has been collected manually or has been collected by the facility and estates managers. And the main idea is that the graphs are looking and are quite complex, so they're not meant to be viewed. But the main idea is that we can write queries like, give me the sensors in this room. And that could be interesting if, for example, one was looking at understanding comfort, ventilation, or other issues. Or give me all the sensors that belong on the first floor, or give me all the vertical movement devices in the building. So one can write that query once, and then they can write it for different buildings and get a report back, which is the information which is required. The last bit, which I will focus on, is that process tends to assume that that organization of information brings everything together, but that might not be consistent or might not be coherent. So rather than doing model checking at the ingestion, which we're doing, looking at how our model is structured, we can also be slightly more agnostic, and then once we have the compiled knowledge graph, ask questions related to, for a specific service or for a specific application, do we have all the information which is required to commission and deploy that application, or what would be that information? And the way we approach that is using something which is called SACL, which is essentially constraints on the graph or questions on what the graph should be. And I have put here a very simple example. For example, every data point should be linked to a time series reference. And this is a very simple example, right? And so we could have different manifestations of requirements from the different applications. This is a very simple example, but we can have more complex and several SACL queries. And then we can represent that within the integration middleware. And when an application gets registered into our framework, is able to ask and see if the available data points are available. For example, a forecasting service might need data from an energy meter, so it can query, does that building have an energy meter? If the answer is yes, does that building have data for that energy meter? If the answer is yes, of that granularity, then that service might be deployed and run. And basically, that can be done using that same idea. And so what we're looking is ways of bringing that, working with uncertain data, and then delivering the whole framework so that we can do it not for 1 building, but the 10 pilots, and hopefully scale that up to more than 10 pilots, assuming we can generate those graphs. And so we move to the second one, which is BuildON, that Flavia is going to be talking about.
Yes, exactly. So we have been using some of the tools that Dimitrios proposed within BuildON, but BuildON goes a step over and also provides the whole architecture, how we can leverage those semantic models to actually allow the portability of applications, and what are the other elements that should be included in these architectures so that we allow the controls to actually be implemented in real buildings. So BuildON, just as a summary, is a project that is being coordinated by Sofia in Cardiff. It has 20 different partners, 9 countries, 5 pilots, mixed in residential and non-residential ones, and more than 10 different applications, including analytics and control applications. And if we look at the software architecture and what we are proposing for it, is that we want to provide and we want to understand it in this stage of the project, what are all the components that should be included in this middle box here that would allow several applications to interact with different data sources from different buildings. So here are a list of our desires, so what we actually needed from those components that they need to deliver within the project. So we want to unify data access from the different applications to the different buildings. The data need to be contextualized, it need to be easy discovered. We are interacting with different data sources, so we need the interoperability, both technical and semantic. We also need that if we have new data source, that they need to be easily integrated into the whole architecture. We are working with control, so we need real-time response and also data storage because we also need historical data. We need the data to be secured when communicating and exchanged. We also need privacy access controls, and because the applications are on the cloud, they need to be reliable. So we need to have fault tolerance. We need to have short-term storage and everything, and we need to have loggings and all these different capabilities to allow analyzing and getting track of any problems that we might have in the communication. These 3 first list of characteristics and features that we wanted are supported by semantic models. The others are complemented by other subcomponents we are proposing. So to deliver this, BuildON architecture is composed by 5 main components. The first one is for interacting with the different buildings and their data source. we have what we call an edge domain controller. And in BuildON, we are testing the replicability of the whole architecture using and developing 2 different gateways, interacting with 2 different vendors and their products. This component is basically having a way of normalizing the data coming from different protocols so that they can be sent to a middleware. That is the next component on top of this. Complementary to the edge domain controller, that is our gateways on the field, we also have cloud controllers that are basically a component that should interact with weather station, other web service, or even IoT platforms that already have the data concentrated somehow in their platform, and then we can access the data via that REST API communication and not directly in the field with the device. On top of them, so connecting the different DCs, so the different gateways and the cloud controllers that we have, we needed the data access. We proposed the data access and control manager, so this DACM, this middleware, that normalized the data coming from the different pilots. And the DACM is already on the cloud, and it's connected with the data repository that has not only the data storage capability and support within BuildON, but also is where we integrate the data by generating semantic models that describe the buildings. And both the repository and the DACM with the real-time data, they are connected with the Universal API. That is this 3rd level of abstraction that allows the different services within BuildON to interact with the building via a common and unified API. So if we start looking at each, we are going to look at each of those 5 components and see what are their main characteristics and how we have been deploying them on the field. The DC basically has communication with the field device. It has connectors for the different protocols and different accessing data accessing mechanisms from the different pilots. It also needs what we call point configuration. So every time we have a new configuration, a new device, then we need to configure the device and have a minimal set of metadata information about the device. We also have lightweight service, short-term storage, data processing, and the data connector with the DACM. I'll try to go a little bit fast because I just learned that I have 5 minutes to finish. So this is the instantiation of the DC for one of our gateways, where we have the different connectors from the different protocols. The main characteristic, the main focus of this is that we are proposing device-agnostic operation. So everything that happens after having the connector with the different components, different protocols, is agnostic to whatever the device is. The other part is what I mentioned about point configuration. So each of those DCs, they are responsible and should be the point where we have most interacting with the users and have the manual input from the developers for configuring the device and the minimal metadata from each of the device. This information is then forwarded to the other components, so the DACM and the data repository, for understanding the data, mapping the data, generating the semantic models of the building. And the other part that is a key for this edge device is that they need to have a local data storage. And we have a whole rule that defines how the short-term storage should happen. In the DACM that is on top of that, we have a broker basically communicating with the different DCs and CCs, the configuration of the device. So here the key step is normalizing the data. So first normalizing the topics that should be used by the different DCs and CC to communicate it with the BuildON DACM, and also normalize the payloads so that we only have one processing mechanism inside of the DACM to get the message from the different pilots. It should allow a two-way communication, so reading and writing, and for this we also need quality checks. So we need alerts to see if we are out of a certain bound. We need writing protection to see if we can actually change something in the building. The data repository one is the one that I mentioned that communicates with the DACM for connecting with the real-time data and then storing them. And the other key part here is that they should be the ones receiving the information from the DCs with the minimal metadata requirements so that we can generate automatically the graph. So this is basically what Dimitrios was showing. This is one of the source of information we get, is basically the first one that allows us to generate the first partial graph automatically. And the third part of the data repository is the support for the Universal API. So if we look at the Universal API, it basically is the interface between the repository with the time series database and the DACM with the real-time data and the ability to write back to the building and the service. And for this, it has a very close relationship with the repository, where we have a user interface that the service can register the data requirements that they need. That registration of the data requirements is automatically generated and used to generate queries to the semantic models of the different buildings. And using the results of those queries, we have automatically generation of queries to communicate with either time series database, so in this case, the influx QL, but also to generate queries and requests to the middleware, the broker in the DACM. The result of this is a data collection that can be used via an API endpoint by the different service to access the data they requested. We have here just one example. We have been testing this for 2 different pilots already, one commercial, one residential, where the data is being processed, the dynamic data is being processed in the DC and CC, the ACM, and then we have the Universal API here and the repository and an analytical application. So we created a dashboard that is connecting with the building and getting some real-time data from the building. And we also develop a control application, a demand response control application in this other building here. I don't know if we are able. I have one short video. I'll just fast forward it so you can see. This is one of the pilots that we have been working on. You can see the 3D. Oh.
I cannot see. It's not shared.
Can you?
Okay. Now it's okay because it's extended. So.
Oh wait.
I
don't see. Okay, let's see if we can fast forward here. Okay, so that was the 3D model of the building, and that is used for generating a first version of the knowledge graph in this particular case. And then we have here, when we start to register, I think it's model checking. I can't see it very much, but it's the model checking to check if the FC it was complete enough to generate the graph. And if we have any clashing or any problem with the IFC, and then we can automatically enrich and correct them. Later on, we have the registration of the data coming from the buildings, and we enrich the graph with new metadata for each of the devices connected in the building. So we can see here, I think, is the rooms are read with the sensor information, like the metadata about the sensors. And I cannot see where the mouse is, but then the last part should be our middleware application connected with the time series database and receiving already the data from the buildings using the semantic part of it. So that's it.
Okay, thank you, Flavia. Thank you, Dimitrios, for your really interesting presentation. So I think it's time to move to Daniele, that will present you the work and moderate bad ontologies. So okay, sit here, we'll sit here. Maybe it's already open. Check the ones that are open. Yeah, I suppose it should be this. Yeah? Yep. Good. So, the floor is yours.
So, good afternoon, everybody. My name is Daniele.
Presentation mode. And microphone up close.
Okay, do you hear me?
Okay.
Okay, perfect. So, good afternoon. My name is Daniele Antonucci. I am a senior researcher on EURAC Research Center, in particular on the Institute of Renewable Energy. EURAC is a research center located in the north of Italy, and in particular, I'm a researcher on the group of energy efficient buildings. And today I'm going to show you, so we are talking about ontology and semantics and the importance to have it, but also how it is possible to use a large language model to create ontology and semantic for data-driven building service. So my colleagues before said a lot of things to when you're going to generate an ontology for buildings, there are several positive aspects, such as standardization. So most of the time you can just standardize the description of the buildings, in particular considering that each single component is described in the same way. There are reliability, so all models are developed using the same format and language, so we can reduce a lot the error. Scalability, so it's possible to improve and obtain information about the building and system more easily and faster. And also there are other controlling and simplicity, so there is a very clear division between metadata and data. Even if there are these positive aspects, there are also negative aspects. So I want to say it's not so easy to generate and create a file that is based on a specific ontology. In particular, there are also different formats. Using the graph database, the format that we are going to use generally is it's a RDF file with a turtle format that is not so common on the to be used comparing to SQL, JSON file, and then so on. Also, this file needs to be updated. So there are several versions of models, the standard models available on the market. So you need every time to update it, and it also, in this case, it requires times. And probably the last one is very important because it's to create it, there is we need two specialists. One that is an IT specialist that is able to understand which is the ontology and how to create it, and after the energy manager that is the ones that knows the characteristics of the building, so how the buildings behave, which are the components that characterize the buildings, and sometimes these two figures don't talk together or they have different consideration about their work. So what we try to do in Moderate, in particular, the approach is try to simplify the creation of the ontology model using a large language model. In this case, reducing the gap between IT and energy manager, as I said before, and also enable the use an easy updating of the models using the large language model. So every time you just have created your model, you can update with a new version very, very easy. We call it this brick LLM because we are using a brick schema as a reference standard model. In this case, we are using some technology specific related to the creation of application using large language model, for example, LangGraph. And in particular, the tool is based on LangChain framework that it's able to help you to choose between different large language models. So far, we are using ChatGPT, but there is a possibility to move with the other type of languages. So there is Gemini, even if there is few issue with the Gemini in Europe, or Llama from Facebook and Fireworks. So there are several Claude. So there are several LLM that can be used. But for now, we are using ChatGPT, in particular the API of ChatGPT. So the brick ontology, I don't want to go much more in detail because, okay, we said before it's a specific description. So it's a file in which there is a lot of information about the components that characterize the buildings, and in particular, these components are connected together like in a graph, and there are different categories. So there are some macro category, and after go ahead to the category that are small, so such as simple elements. So starting from the building to the single type of sensor. So in this case, what we had done is said, okay, we started with a prompt in which we ask to the user to just provide an information about the characteristics of the building. So for example, I am, in this case, it's an example. I am an energy manager and I'm going to install a monitoring system for my building. So this building is located now, just for example, in Luxembourg. So there are 3 floors. In each floor there is 1 office. In each office there are 2 rooms, and now I'm going to install 3 sensors in each in each rooms. And after, I can associate this room to a specific unique identifier that is the connection to the dataset. So the sensor send the data to the specific time series database having this unified ID. So the tool starts with the part, there are several different nodes. So start with a macro category, as you can see here, and after try to identify that we call also parents, and after we are going to identify the children. So for each single macro category, we check and which are the different children that are available in this category, and after we go ahead to the relationship. The tool generated the schema, and after if there are so if the model is able to find out the elements, the sensor, so in this case, ask also which are the unique identifier connected to this sensor. And this can be done in 2 ways, or directly writing on the prompt, or in a second phase when the schema is already done. So we are going to ask the unique identifier. So now I'm showing you just how the tool works. It's a short video. You see, I think yes. So we are using LangGraph Studio. In this case, we have uploaded our scripts, and I think it's very good because it's able to check each single steps, which are the results for each single steps. Now in the prompt, we have I just write the text that I showed before in the previous slide. And here now the tool is able to find out all the sensors and to get the relationships. After the definition of the single relationship and the connection between elements is going to write a schema, a turtle schema, that now we can validate in 2 ways, using building motif. Or PySQL, and understanding if the results can be useful, can be used or not, or if it needs to change something. So this is a preliminary work. So the tool generate the file very easy way, particularly if the description is not so complex. And as you can see here, at the end, we have a specific output, and in the output there is this file, this dirty file. As you can see in the, here, so the tool identify the different elements, so office and floor, and also connect together all the single elements together, and also the sensor will be connected to the specific place. For example, in this case, we have a temperature sensor that is located in room 3 with a specific ID, and the model is able to understand this information. There is also another point that the user doesn't provide information about the database, but due to the fact that there is this information related to the ID in the prompt, he put an example of the name of this database that after the user can change it. So this is an example of very, very simple about the information that is possible to so create using a very simple description. If we just make some much more complex information on the prompt, so for example, we are going to give information about latitude and longitude of the buildings, where it is located. So I mean, where it is located. Information about there is much more sensor, only 2 floors. There are only 2 flats with 4 rooms, and only 2 rooms can be monitored with 3 sensors. And after there is a photovoltaic systems and also electricity meter connected to this photovoltaic system. And after there is also the information about the name of the database. In this case, also the tool is able to understand quite well all the comps. Now this is the other example. So it requires now much more time, like 3 minutes, but I just cut part of the modeling of the processing, because there are much more information, and he has to check every time this information. Going node by node is going to check all the components. I'm going to just, I don't know if it's possible to move on, okay. But in just 3 minutes, in this case, you can have your model already available. One of the points is that if we generate a very long prompt with several information, probably we don't have this very clear file, but probably we have some error. So in this case, for example, as you can see, the model is able to understand the sensor, where they're located, which are the ID. So connect the ID to the database, and connect also the sensor to the point in which it's located. So in this case, the room. So it's possible to see for each single sensor. But okay. Sometimes someone can say, okay, you have created this, but you can just copy or use directly ChatGPT. So I copy my description, I put the description in the prompt of ChatGPT, and after I ask him to create my file. I found out if this file is good or not. I tested, so I did also the same prompt, but if you see, so it is not able to create a good file. So there are several errors. So for example, is going to use also other ontology and not consider that most of the aspects are already available in Brick. So it's going to connect a floor to part of project, but project is a flat. So there are several errors considering the approach to put only the test on ChatGPT and ask him to create this file. This is why also we created this application. Sorry, but yeah, I would say all that glitters are not gold. So it means that it's not always perfect. So sometimes, I said before, if the description is very, very complex, probably the relationship are not so good. So it is not able to find out very well all the relationships. And in this case, I just advise to divide the description in different parts, and after create different, I would say, some models, and after connect all together. Or in particular, to use this type of tool, you need to connect to specific API of the large local model, and it takes a cost, so you have to pay, and depends on the type of large local model you're going to use, but generally there is a specific token that you are able to get according to the money that you can spend. So it could be a problem, or to overcome this problem, you can just, for example, try to train your local model using Brick, but there is in this case another problem, that is you need several Brick schema, and after you have several models, you can train very good large language model. But in the other case, I suggest to use only the big ones that are available now in the market. Okay, now the connection. So as you have seen also in the previous presentation, all the files will be connected to a timescales, to item series database. So we have done the same. So we created the ontology for specific pilots. We connect these pilots to the timescales, and after on the top, we just created a simple API using function that we have created tailored to the specific pilots. And this is just an example in which we have, for some shops in Italy, we have created the ontology, we connect the database, and after we created this, this API and connect to the benchmarking service. Next development, so this is the first part of the overall work that we are carry on. So one part, as I said before, is the creation of the ontology, and after the last part that we want to create is use a large language model to retrieve data. What this means? It means that now I have the model, I have the data, so we want to create a specific application in which the user can just ask an information about, for example, which is the average of energy consumption for my whole office located in Luxembourg. And after using the model, we are going to filter the information on the ontologies that we have created, get the data from the time series DB, apply the analysis, and generate a response. All this information only using a specific LLM. That's it from my side. So thank you so much. Yeah, I leave the floor.
I understand how difficult it is to keep the time because there are a lot of things to say, to tell to the audience. So I understand. Let's try to keep the timetable because otherwise we take the risk to skip the coffee break, and it's under your responsibility, you know. So it's time for DEDALUS. Jose from Cardiff. So welcome. The floor is yours. Jose is going to present again about ontology and the context of data response and flexibility modeling for interoperability.
Okay, hope it works. So, good afternoon, everyone. So, as Diego introduced, thank you very much. I am José Hernández, but I would like to say that I will talk on behalf of my colleague Susana, who is the leader of this part in the DEDALUS project. And basically, I will follow the same line of the previous speakers about interoperability, about how to use data models in order to assure the data is being shared. So that's why I will try to be shorter, and I will try to keep in time. Okay, basically, I will formulate a bit the problem, even though my colleagues of UCL has explained very well the problem, really. How we are implementing in DEDALUS and why we are selecting the data model, I will tell you later. And how this DEDALUS ontology is being used in the context of the project. So basically, our problem is that, as previously introduced by UCL, we have some problems with the languages. We have different languages. We have different formats of data. So you can imagine we have English, we have Spanish, we have German, we have Chinese. We have different formats of data. But we need to communicate the data with the services, with applications, or whatever. So at the end, we need to create something that is able to understand that we are talking in English, but also in this format. And that in this case, in Chinese, 15 means 15 degrees Celsius. So this means semantics, as mentioned before by Flavia. So all these things should be solved. Still, we have this kind of problems in the context. For this, let me take the one slide from Espresso project that defines different sets of interoperability aspects. We have, first of all, the foundational interoperability. It means northbound and southbound interoperability. Southbound meaning for the data sources that we need to integrate within our services and our projects. Northbound about the APIs to share the information for the services and different contexts. So in this sense, we have in the middle the data lake containing all the information, all the data, and this is we can say the middleware and also the repositories of data that are used for the northbound and southbound interoperability aspects. But we have also the semantic interoperability, so this has been explained already, so we need to understand. But I would like also to highlight the structural interoperability, because the structure of the data is also very important in order to transform the information in the ETLs that previously was mentioned by Dimitrios. We need also to transform this information, and we need to know the structure of the data. So basically, what we need for the interoperability is to define open and standard protocols to gather data, southbound interoperability, open and standard protocols to share the data, northbound interoperability, define the structures for the data exchange, so common structures to share the data, and define languages and vocabularies in order to share the data. And how to do this is thanks to an ontology. So why the ontology? First of all, because I will be very short in this aspect, because it was explained very well by Flavia before. We need to create some application. In this case, DEDALUS is focused in demand response programs. So the services that we are working on in DEDALUS is about demand response, and then to create these portable applications for demand response in different contexts. So that's why interoperability is very important in this project. So we have different buildings, we have an application, and we would like to deploy the same application in different buildings with the context that they have these buildings and so on. So for this reason, we need to generate these data models for the buildings. We need a metadata information. We need to know the building systems that we have. We need to know the data models, and we have, on the other hand, the time series data and the IoT platforms that are collecting data. In this sense, having this methodology or this schema to work, we can semi-automatically configure the demand response applications, because we will have the same demand response application. So as Flavia mentioned before, develop once, deploy multiple times, to configure the same application for different purposes. So the demand response application number 1, number 2, number 3, dependent on the building that we have, and of course, using the common data model that we have defined. And last but not least, execute these demand response applications and run in the different pilots of different buildings. So this is more or less what is the formulation of the program, the challenges that we have. And how we have done this in DEDALUS. Basically, first of all, we have started with the state-of-the-art, with different standard data models. Some of them have been mentioned here, like Brick, Big. We have also Saref, OpenEDR, but also DCO. We have extracted the pros and constraints that we have in the different ontologies in order to determine the capabilities that they have for demand response programs. So we should keep in mind that most of these ontologies are quite open and quite covering a lot of aspects. So that's why we need to define which are more focused on the demand response programs, and then select the most suitable ontology for our problem. And last but not least, to extend this ontology. So it's true that these ontologies are covering a lot of topics, but not all of them are covering demand response programs. So in demand response programs, there are still some gaps that need to be covered. Just to summarize the state of the art, so we neglected these 4 ontologies. Basically, Saref is not covering flexibility; it's more in the part of the smart appliances and systems. OpenEDR, we detected that there are more generic concepts that are missing, so we decided that this is not the best option for the project. Brick is very focused on buildings, not in demand response programs. That's why this is also discarded in this project. And Big is really, let me say, big again, and difficult to follow. So, and is more focused on energy performance certificates. So that's why you can assume that the selection was DCO, because it is covering the most part of the demand response programs. And later on, I will show you some insights on it. But how the ontology and the demand and the interoperability is taking part in DEDALUS. Basically, you can see here in the knowledge, we have a knowledge layer where we have the DEDALUS ontology that will be able to connect the south part of the architecture where the data is coming, where we have different profiles, we have the IoT agents, we have the local platforms, and so on. And we have on the up part the added value services. So in this sense, this knowledge layer is the one that is translating all this information, adapting this information in order to provide these services. As mentioned before, our main focus or our main selection is DCO. Here you can see the main schema of DCO, so I am not going to enter in the details about DCO. This is a reduced schema of DCO. But you have to say that even though we say that we discarded Saref and this kind of ontologies, DCO is based on these ontologies. So you can see that the, DCO has some Saref entities. There are other entities for brick as well. So they have some, they have summarized like the previous ontologies in one that is more focused on demand response part. However, as I mentioned before, these ontologies are covering a lot of topics. So we did our requirements match, in this sense, determining which are our services in demand response and which are the real needs that we have from the entities that DCO is offering us. So we are reducing the complexity, so this means simplifying the development and deployment of the services, using less entities and using the entities that are really needed for the demand response programs. But not all the entities are covering all our needs. So we need to extend this ontology. And for that, we have some entities that you can see on the left and right part of the DCO ontology that we need to include. For instance, the KPIs were not included in DCO, so we took the big ones from in this case. We also use interconnect user preferences for the demand response programs. We should remind that users are key in any demand response program, so that's why the entity user is very important. For instance, we detected that there are no inverters in the device module of DCO, so some entities that are really needed in this kind of programs. And how we're going to use it within within DEDALUS. So basically, in DEDALUS we have a fireware-based implementation. In this case, with the colleagues of engineering that also are part of this presentation. Basically, fireware using NGSI version 2 information model. And so you can see how it is related to the different entities, attributes, and metadata that the model has. And here you can see the schema for the information model that from NGSI-LD, sorry. So we are taking this as base for our development and how to use it. So fireware is basically using different IoT agents. If you remember previously in the architecture, I mentioned that we have the different IoT agents plus the knowledge layer that is covering the data model. So in fireware, we are able to create our own IoT agent. So a custom agent is being developed to represent this DEDALUS ontology. So covering the data flow from the data sources that we have, the raw sources that we have, until the added value services that we have on the other hand. So in this sense, covering different protocols, like you can see here in the schema, like MQTT, OMA, Ultralight 2.0, and our IoT agents together, the context broker and the knowledge graph that we have with the data model, we are able to provide the northbound interoperability for the services. So basically, this is a work that is ongoing yet. So this is the concept and we are working on it. So we have some kind of small demos to be for the starting point. Here I don't have any demo, but we have some demos. And just to conclude, because I know that I'm very, very fast. So let me recap that interoperability is key. It's true that we have had 4 presentations in this session, but again, interoperability is key, and we didn't solve interoperability yet. There are a lot of projects, there are a lot of initiatives, and we have a lot of data models, so we don't have any consensus about the interoperability. So we need to still have a consensus, work on it, and collaborate a lot in the different projects for this interoperability. In fact, interoperability is being developed in many aspects, in many services, in many topics like buildings, but demand response and flexibility is something that is still has some current gaps, and we need to cover. In this case, in DEDALUS, we are doing. And this interoperability is key for data management and sharing data. So data is the oil of this century, and we need to work with data. And we have data without meaning. We are not going to do do nothing. Of course, making this data accessible for all the developers and in terms of services, the facility managers, the decision makers, and so on. And with this, I finished 12 minutes.
Thank you. Thank you very much also for the speed.
Yeah, I have been very, very quick, I know.
Okay, thanks. So it's time to go to the second session. So the first part of the second session, because in less than 25 minutes we will have our coffee break. So now we start the session for data-driven smart buildings and services for advanced energy efficiency. And the first presentation is given by Christine Grich for Blueprint. And this is work that is being done in the DEDALUS project again. Thank you, Christine. The floor is yours.
Thank you, Diego. Do I have to open it here?
UCL.
Ah, yeah, of course, it's here.
Okay.
Okay, thank you.
Great.
So thank you, Diego, for introducing. I will also make it quick so we can all go to the coffee break. Welcome to the session B. And let me start here with a little bit of a different topic. So I will explain today how in the DEDALUS project we developed a social science framework to also develop new services in advanced energy efficient buildings. I have to say that the social science framework, so we at Blueprint were the work package leaders of this work package, and Smart Innovation Norway, our great partner, did develop the social science framework and put it also into action together with Domex Engineering and our partners from NTUA. So let me start with just telling you what DEDALUS' overarching project goal was. The goal is to deploy a social, technological, and business framework to design and demonstrate a social science and humanity-driven demand response ecosystem. And we are focusing on optimizing and managing automated demand response in residential buildings. The social arm in this was structured through a social science framework, which had its insight areas on behavioral change theories, motivation and behavioral economics, and the pillars, individual context, goal setting, and motivation. I will talk about that later a little bit more. And as you might have seen in a couple of other projects here at the Sustainable Places Conference, these social science frameworks are here to bridge the frameworks with the tool application. And we do that for the goal of fostering end-user engagement in demand response. So basically, it's like we had the experience before that the tools were developed, but not really used by the end users. So this is an approach to take social science theories together with the co-creation with the end users themselves, and therefore have a higher engagement into demand response. So here are the pillars I was talking about before, like the individual context, which are mainly beliefs, values, and knowledge of the end users, and goal settings, which is a theory that starts with if end users are setting a goal they really want to achieve, it's going towards a positive behavior to demand response participation. Also the motivators, how are we doing that, or how did our partners do that? By investigating questions like what are the barriers and drivers related to residential demand response. Also which incentives, monetary, non-monetary, are most applicable to consumers to have said goal really set and achieved, and also which nudging interventions are most effective. So all to increase the motivation in a positive way towards demand response participation. So here we have a table where you can see how the partners were doing that. So, for example, for the pillar individual context, there was a segmentation questionnaire handed out, and with this segmentation questionnaire, they defined personas per pilot. I will tell you a little bit later a bit more about the pilot sites and how different they were. Here, the second pillar would be the goal setting, and they did the co-creation activity was barriers and driver workshop based on a COO methodology. With the pillar motivation, they did nudging and incentive workshops, and the methodology behind that was like user testing, make exercises, focus groups, scenario analysis, and so on. Sorry. So the main part in this work package or within the social science framework was also that you would have workshops with the pilot sites. So the partners designed the workshops to assess the factors within the social science framework, like the COO method to assess barriers and drivers, and the ranking test to assess incentives. And there were a lot of nudging activities to assess motivations and also preferences regarding tools and services. And of course, the output would be, well, to understand the end user better in terms of motivation, preferences, and needs, but also to have recommendations for broader engagement strategies. And of course, always learning and best practices. So let me tell you a little bit about the end users. So these are the pilot sites that we had in DEDALUS, and as you can see, it's the main use case of each pilot site is very different from each other. So for example, in Austria we would have the flexibility pre-aggregation for building level energy community, whereas in Romania we had the blockchain solution for demand response management and flexibility aggregation. I won't read you everything, but just that you see as different as the use cases were, as different also were the end users that we had the co-creation workshops with. For example, in Italy we had mostly elderly people, whereas in Romania we had, for example, students. So just that you know, that helped us very much to have different personas throughout the whole project. So here you see a couple of pictures for the workshops. I think these were in Greece, Italy, and Austria. And on the right side, you see a couple of materials that the workshops leaders were asking feedback on. And this slide shows the analysis. So we would have ranking tasks to determine incentives and the user motivation profile to have based on the COO methodology, and also the app feedback. Where in the DEDALUS project, special attention was given in the design of new mockups for the nudging interventions. Every pilot site designed some new nudging techniques that were provided to the end user for feedback, with additional comments also that led to quite some changes in the end of the app design. Let me tell you something about the consumer segmentation quite quick. There was a questionnaire circulation in person or via email, of course. And here you would see a flow chart how the segmentation, like the segmentation approach was. So first you would group the responses strategically, so the questions would be like demographics, energy behavior, energy literature, demand response, familiarity, and so on. And then you would group these responses strategically, and if the population is large enough, you would proceed with a segmentation in meaningful groups, and you would profile a persona per pilot. And with this persona, you would have at the end a couple of suggestions how to reach this person in the best way, so that you would have a positive demand response action. Here you see an interactive visualization dashboard. This is just that you know how some answers were, just to have a picture of how the segments were. And this is an example of a persona in a pilot. And in this pilot, for example, the main end users were women with primary high school education, and they would have a low to mid energy familiarity, but they would have a very high attitude towards the environment. And the main demand response barriers would just be lack of awareness. So how would you approach these persona? And so the suggestion would be that you would educate them foremost educate them just to adjust the educational background, because they would be very positive towards the environment. And then actually it would help to improve the behavior towards demand response, or what they think about demand response. So just to conclude, we would have the social science framework provided insights into the motivations, profiles, and needs of the end user. And we would know in the end what would be the effective incentives for each of the pilot site users, for example, for each of the profile. And of course, we would get a lot of feedbacks on the apps and recommendations for the engagement and social acceptance, and also best practices. And then we would have also positive outcome on the technical components, like we had a more user-centered software architecture. Also, we would have improved user engagement within our technology enablers, and a more effective AI-driven service design. Thank you.
Thank you. Thank you, Kristen. So we have the second presentation of the session. This presentation is given by Sofia Murero, who is coordinator of the BuildON project, and from Cardiff. So now the floor is yours. You have 10 minutes, but you know, if we can take some minutes of the coffee break, I don't think that it will be so dramatic situation we can resist. But I think that if you put in...
okay, if I put it in presentation mode?
Presentation mode, it should be already there. Yeah.
Okay, perfect. Good. Thank you. So I will try to give an overview of the analytic and control services that will be developed in the context of the project. We are still in a very early stage, as the project started 1.5 years ago, more or less. And we have been working first on this interoperability framework that has been presented by Dimitrios and Flavia. However, we are still working on the definition of these services. Next year, early next year, we will have the first release for some of them. So I think it's worth going first to the motivation behind, the context in which these services were defined. We need to take a look into the status of the building stock. We know these numbers about the energy consumption. Buildings are responsible for almost 40%, 36% of the energy emissions. And what is more relevant is that most of these buildings most of them are not compliant with energy standards, and however will be standing in 2050. We can see that electricity demand will continue increasing, and although we will decrease some rates for consumption for some specific aspects, this energy consumption will continue increase in the next years. So we need to know this. Also, take a look into the different initiatives that have been set up from the European Commission, such as the Green Deal and the Renovation Wave in 2020. And we have different milestones set up, such as the interim goals in 2030 for emission reduction and the goal for zero emissions buildings in 2050. What is more relevant in the context of this project is that in 2018, the SRI indicator was included in the EPBD revision, and in this context, digitalization started to have a more significant role. So we have this opportunity to reduce energy consumption thanks to these energy efficiency improvements in buildings. And however, we have the challenge that these renovations are not that easy, sometimes because of these legal and financial barriers. So digitalization needs we need to pay our attention to this and bet for these kind of solutions that are more affordable. Taking a look into the definition of smart building, okay, to consider a building smart, we need to see that users are considered in the decisions, that these buildings are considered also the signals from the external environment, and that these buildings integrate solutions that are advanced in terms of technology. This is what we wanted to provide in the context of the project, and in order to do this, we need to break some barriers. We need to address the barrier of the social aspects, because we have this lack of user-friendly solutions, and users are not very familiar with technology, so usually it's not easy that these technologies are adopted. And we have the problem, what is more relevant, these technical problems. First of all, the harmonization that has been described in the previous presentations. We need to facilitate integration between the software and hardware solutions to work for standardization. And on the other hand, we need to use these new technologies to integrate them to control the building, such as artificial intelligence for energy management and optimization, and digital twins. So this is what we propose in BuildON, this smart transformer toolbox that wants to combine all these solutions and break these barriers, providing different levels of solutions, starting with an analytical level that will help users to understand what happens in their buildings. On top of this, we will have an automation and control level of services. And finally, users are able to access to all these applications through empowerment tools and also digital twins. All of this is set up on top of this interoperability framework to facilitate integration and also to facilitate how we control different buildings and trying to abstract all this complexity that is behind them. So, as I was saying, this is how we plan to break these barriers, considering all these kind of solutions, tools. And if we want to take a look more in detail into the services, which is the name of this part of the workshop, we are providing two categories of services. The analytical layer is covered by the map services for monitoring, assessment, and prediction, and the automation and control is covered by the optimization services for energy optimization. We consider two aspects when we define them. First of all, how we want them to impact on the building by integrating these technologies in order to provide higher levels of automation, and consider also the needs of the stakeholders, the environment, as mentioned before. How we want also to foster this adoption. we want to go a step further also in the definition of these services, trying to reduce the complexity on these interoperability aspects, and that's why we are working with an archetype-driven definition. First, we are going to look into the services that are provided in the context of the project. When we define them, we try to calculate how they will impact in the different SRI domains and SRI impact scores. And this is the results that we have. We have some numbers, general numbers, considering all the pilots. And as we are applying them in pilots from two categories, residential buildings and tertiary buildings, these values are also split below. Starting with the analytical services, the first category covers energy assets monitoring and benchmarking, and in this context, we are providing advanced visualization and benchmarking solutions tailored to the different building categories. So this way, we are contributing mainly to this, the monitoring SRI domain and the information to occupants SRI impact score. In terms of the second category, the building energy fingerprinting services, we are providing solutions for energy profiling, advanced forecasting capabilities, and for operation and maintenance. In the case of these services, we have an impact on the same domains impacts as mentioned before, and also to the maintenance impact, as we have these services applied, this category of services, the operation and maintenance, are applied in the tertiary buildings. Now we jump into the automation and control services. These services are split into three categories. The first one is the user comfort optimization strategies, in which we are providing services for visual comfort and indoor environmental comfort in order to improve occupant well-being. As we will see, the main impacts that are covered by this category of services are energy efficiency, information to occupants, and in a non-direct way, we are improving the comfort, convenience and health. This is done by all the services from this category. About the domains, here we can see that we are also improving the heating and cooling domains, cooling only for tertiary buildings, and the lighting domain. The next group of services in this category is the assets control services. We are here providing strategies for energy assets controls for heating and cooling generation and enhanced management. Again, having an impact on the heating and cooling domains, and also the serving paths for energy efficiency and information to occupants, and the other ones that were mentioned before. And finally, we are also providing services for energy flexibility, in this case for occupants and grid congestion management, now covering the domains for electricity and electrical vehicle charging, and the impacts for energy efficiency, energy flexibility, information to occupants, and the ones that were mentioned before. So somehow we are covering most of the domains and impacts. However, these services will be applied in a joint way. So after the project is, all the services are running, we will be able to assess how they are really impacting in our pilots. The last point that we were mentioning about these services is that we want to go a step further in the harmonization process. That's why we are working with this archetype-driven definition, in which we define an archetype as a model that is able to capture all the essential characteristics, functionality of the different energy assets in the building. We are working with entities characterization for the buildings, splitting four levels and a hierarchy of 4 levels from building to space, equipment, and point. And what we want is to be able to harmonize these developments with the developments provided by the Universal Building API, and facilitate how services are applied and how we can add or delete entities that are considered by them. The benefits of this approach is that we will be able to provide customized services considering different environments, to adapt them very easily, provide these robust solutions that can evolve in time. So to conclude, I wanted to highlight some remarks about what has been covered from BuildON. So we need to bet for digitalization. This is the driver that we have in order to work for this harmonization, be able to reach this increased level of optimization. But we need also to consider that users are part of this transformation, and that we need to consider also all the signals that may come from the environment. This way we will be able to promote new policies, maybe standardize some of the solutions that we are working on. And that's all from my side.
Okay, thank you.